1.5. You're good.
Welcome to the Fall Infrastructure Council meeting. It gives me my great pleasure to welcome you here both in present and via the web. I'm the chair of the Infrastructure Council this year and am pleased to serve in that role. I'm very happy to introduce our speaker today, Professor John Gulliver, who really needs no introduction. He's a professor in our department, a past chair of our department, and also he is a resident of the Institute on the Environment. Professor Gulliver is involved academically in both water resources and environmental engineering areas. He's got a very active research program and is really one of the innovators with permeable pavements, which is the subject of his talk today. Just a little bit about his background. He's got his bachelor's degree from the University of California in Santa Barbara in chemical engineering, and his master's and PhD degrees were from the University of Minnesota. He's taught courses in fluid mechanics, environmental mass transport, urban hydrology, water quality, and our capstone course, which it tops off our undergraduate program here at the University of Minnesota in civil, environmental, and Geo Engineering. And so without further ado, I'd like to introduce Professor Gulliver.
Thank you, Kathy.
Oh, sorry, you don't need that.
No, I don't. Thanks. I'm going to talk about permeable pavements. Hopefully everyone can see the slide. We don't have very good control over the lights in this room, so either it's totally dark or it's lit like this. Permeable pavements are not really used very much in northern climates. The reasons are obvious. Actually, you have minimal binder with permeable pavements, and so if you have a freeze-thaw situation, the freeze-thaw could pop that aggregate away from the permeable pavement, and you have a mess lying over your road. So people are a little resistant to use permeable pavements in Minnesota. I hope that what you're going to take away from this presentation is that, number one, a well-designed, well-constructed, properly constructed, and properly maintained permeable pavement is definitely a possibility in Minnesota. We have examples of that. And number two, there are compelling reasons to use permeable pavements in Minnesota. So those two things I hope you take away. If you take nothing else away, that would be good. I'd be happy. So I'm going to give you a little bit of review. Many people know this stuff, but I'm going to give it to you. Oh, I need to mention, Lev Kazanovich and I are co-PIs on this project. It's not just my project. Lev is here. He did the structural side of permeable pavements, and I did the hydraulics side, and we combined our efforts on the rest of it. So I like to talk about permeable pavements. There's porous asphalt, which is, I think, a little bit of a misnomer because all asphalt is porous. But that's what they use. They use the term porous asphalt. There is pervious concrete right here. I'll mostly be talking about those two. There are permeable pavers where the spaces in between the blocks are permeable, kind of some sort of permeable material. And then a separate category is permeable articulated concrete blocks, which are just permeable pavers held together by some rebar. And they're a separate category because in our project, we had someone from the permeable paver concrete from the Interlocking Concrete Pavement Institute, and they didn't want to have articulated concrete blocks be part of it because they aren't part of the ICPI. So we gave them a special category. One way to solve that problem. So a cross-section, full-depth permeable pavement. I like this picture because it's kind of descriptive. You can see the size of the car here. You have 2 to 4 inches of permeable pavement, some aggregate underneath it. The water goes right through the permeable pavement quickly, hopefully quickly, goes into the aggregate, sits in the aggregate, and then soaks more slowly into the subbase. This filter fabric is, I don't think, really necessary. If you do need to use a filter fabric to keep the subbase from moving into the aggregate, you probably want to make sure that it is fairly porous, because the last thing you want is filter fabric at the bottom of your whole system clogging. And so they always put filter fabric at the bottom, and sometimes I wonder why. The other thing about this is that you want to store roughly in Minnesota approximately 2 inches of water. Well, this looks like about 3 feet of stone here, 40% porosity. 2 inches of water only requires 5 inches of stone. So this, and typically people over-design the stone with 12 inches and sometimes 18 inches. So this is way too much stone. You have much less aggregate than that. It'd be about that deep, and that would still be an over-design. A conservative design. So the project scope was we did a literature review, structural, kind of covered all these topics. We did cold climate case studies. We did 9 cold climate case studies, and that would be from the literature. We found these cold climate case studies in from interviews and talking to people. So we published those. We established some research needs, and we developed a software to determine the feasibility of permeable pavement. I'm going to talk mostly about these two here: cold climate case studies, literature review, and move some of the research needs in here where appropriate. I'd like to talk a little bit about the benefits of permeable pavements. There are many of them, and they are significant. They're related to safety, water quality, noise reduction, and I'll talk about one a little bit more here. So volume reduction is for volume of water quality. That's taking the pavement back to the way that we handled water with forests and things like that. The water soaked into the ground and then moved through the ground to a stream or a lake. And it didn't hit the surface and then run into a storm sewer and then run straight to the lake. So it slows down the water quite a bit, and volume reduction is a big deal in stormwater pollution prevention. Improved water quality, that's pretty small, but you improve the water quality if you have water running off. You improve it by filtering a little bit of the particles. Hydroplaning resistance is huge for safety. Spray reduction, you can see the spray reduction here. I hope you can see it because it's pretty substantial. You hear this truck, you can hardly see the truck with the spray, and here is on permeable pavement, it looks just fine. It's said to give a smoother riding surface. I personally do not know that. I've never experienced that. I haven't experienced less smooth riding surface, but I don't have any experience with that. And it does have noise reduction. Noise reduction is substantial because the pores in the pavement will absorb the tire noise. So it really has noise reduction. These are all reasons that apply across the country, and these are why it is implemented to a greater extent in the southern states, Texas, Florida, states like that. The last one is a reason to implement these things in Minnesota, and that would be, can you get by without winter salt application? We have chloride impairments. In Minnesota, salt is sodium chloride. The main reason that we have chloride impairments for our water bodies is because we're pouring so much salt on our roads in the winter. We have to take care of these chloride impairments. And there's really no answers to do it right now. Can permeable pavements provide an answer over the long term? That's a question that we're asking. So I'd like to start now with the keys to success. What we found as the keys to success are, first, a proven mix design. Mix is always important. Like I said, binders are very important. Proper construction, that's also very important. A good hydraulic performance, which is fairly straightforward and easy to take care of if you just do your homework, do your due diligence. And proper and regular maintenance, also fairly easy to take care of if you are careful about it and you do your due diligence, you understand how to maintain these surfaces. Permeable pavements are a fairly new surface, as most people know, as I'm sure all of you know. And so we don't have 50 years of experience with them. So everything that we do is going to be something a little bit different, a little bit new, trying out a new process. We don't have the proven technology of over 50 to 70 to 100 years. So to a certain extent, we are moving into a new technology. So there will be failures and there will be successes. You have to expect that. You have to anticipate that. Mixed design, well, I mentioned this, there's less binder. And so the binder is very important. You really want a good binder. You want to improve binder performance. Maybe graphene will improve our binder. The graphene that two professors in the civil engineering department, Professor Leong and Professor Lee and Professor Marastino are working on. Other improved materials to improve the binder performance would be good. If you have asphalt, you need to consider low temperature cracking and rutting, but you always need to consider that. For concrete, you need to consider freeze-thaw durability. Construction is an important part of the process, and you really have to be careful with some of these things. You have to be careful with the compaction. You don't want to compact you don't want to compact the whole thing, and you don't want to compact even one layer with too much compaction because you lose your void ratio. You lose your voids. And if you have one small thin layer, that kills the whole process. So you want to make sure you handle the compaction properly. You want the void ratio to be appropriate throughout the pavement. And curing is very important for permeable concrete. Hydraulic performance is, I think, fairly straightforward, but maybe not, because pavements suddenly have a new thing, and that is they have to infiltrate the water down into the ground. And so suddenly people who design pavements are talking about infiltrating water. We do know something about how water infiltrates. Surface infiltration rates decrease over time, but are not limiting. I mean, look at this concrete, permeable concrete right here. The water is pouring onto it, and the water is dripping right through. Infiltration is maintained throughout the winter. That's something that surprised me until I started thinking about it. It takes a lot of heat or a tremendous loss of heat to freeze water. Water doesn't freeze automatically. By the time the water moves through this permeable pavement, it's not going to freeze. I don't care what temperature you've got if it's moving through. It will freeze if it's stuck there, but if it's moving through, it's not going to freeze. So if you keep things open and you maintain it well, then you probably will not have a problem with freeze-thaw. And the subgrade permeability is essential. I mean, you don't want to have a lake underneath your pavement. You want the water to be moving through and moving into the subgrade. And then maintenance. Well, maintenance is not that much of a science, but you want to maintain it properly. There is a proper way of doing it. The major cause of clogging, what we found, is a reduction of void space, and that would be either through a heavy load on the permeable asphalt, or through organic particles, or through lack of maintenance. And you want to minimize run-on. That would be run-ons from other catchments. If you have another catchment that's kind of pointed towards your permeable pavement, you want to incorporate that into your analysis and probably try and eliminate that, because it will carry sediment with it, and the sediment could clog your pores. So I got another slide on maintenance here because it is fairly important. Particle removal from the surface is a major issue. If you have a sidewalk or something, then you could do pressure washing at 45 degrees. But if you have a road, then you're talking, or a parking lot, then you're talking vacuum or regenerative air sweepers. They're the most effective. You do not want to use a brush-only sweeper because it just moves things around and pushes it down into the pores. you want to pull that stuff up somehow. A regenerative air sweeper works by forcing air into the pavement and pulling it out. So it forces air over the pavement and then pulls it out. So it works with a pressure and a vacuum. Vacuum sweeper is just providing a vacuum. You want to clean multiple times per year, but everyone should be cleaning their pavements multiple times per year. Because whatever you drop, whatever you have falling on their pavement is going to end up in a storm sewer. That storm sewer is not the end of the line. The storm sewer goes to a lake or a river or a creek. So what you see on your street ends up in our lakes, in our creeks. We want to clean that. We want to get that before it gets down to the lakes and the creeks. That's something I wanted to point out here. So I'd like to go over some case studies. We analyzed 9 case studies. As I said, this was through conversations, through looking at reports, looking at plans, a number of things like that. And they were pretty good case studies. We had 5 in Minnesota and 4 across the country, 1 in Toronto, 1 in the state of Washington, 1 in New Hampshire, and 1 in Denver, Colorado. I'm mostly going to talk about the top 3 here: Min Road, Woodbridge neighborhood in Shoreview, and the paired asphalt intersection, Robbinsdale. All of them will tell us something. They'll all give us some lessons learned. And these are all successful permeable pavements. Actually, all of Minnesota has successful permeable pavements. We do not really have a big failure as of yet. Some are performing less well than others, but they're all performing, and they're still permeable. So the Min Road test cells were constructed in fall 2008, so it's 7 years since they were constructed. These numbered cells here are the permeable pavements on the low volume road. You can see the truck here, I hope, running around the low volume road, and these 2 here are on the main highway. They had permeable asphalt, permeable concrete, over a clay subbase and over a sand subbase. And a test section to compare with all 4 of them. So the lessons learned from that Min Road test cells. I guess these are the ones that I thought were important. There were lots of lessons learned actually, but these are the ones that I thought were probably the most important or the most significant to me. And the first was there's a reduced temperature gradient and less freeze-thaw cycling with permeable pavements. I found that to be interesting. Secondly, vacuuming can reduce raveling. If you vacuum enough, you pull the particles out. And particles and blocking the flow paths is one of the main causes of raveling on the surface, where the aggregate loses its surface cohesion. A sandy subgrade seems to function better, and that's because you don't want, like I said, you don't want a pool of water under high rainstorms. You don't want a pool of water sitting underneath your permeable pavement. And snow and ice appear to melt more quickly on permeable asphalt. Also an interesting conclusion. The next case study is a Woodbridge neighborhood in Shoreview. It was constructed in 2009. Here you see people, the construction crews. Obviously it was a case study for the construction team. You can see all the people around, and I don't think you normally have that many people laying some permeable pavements. But they brought a lot of people out, and they took a look to basically try different things and see how everyone else was doing it. And there are lots of engineers there seeing what's going on. Some of the lessons learned for the Woodbridge neighborhood are: first, construction practices and curing are important. This is for permeable concrete. For curing, they talked about placing an important item was placing a saturated curing blanket on top of the freshly packed concrete worked well. The concrete did not have any sort of cracking or spalling problems after that. And they specified, and this is unusual, most people do not specify, they said the joints should be saw cut instead of with a joint presser, instead of a press cut type of joint. They also said that the reservoir aggregate should be fairly large and angular. They maintain their infiltration capacity by air sweeping every 6 weeks with regenerative air sweeper. They found that organics were the main source of clogging. That would be, leaves, seeds, flowers from the trees. All those types of things were the main source of clogging. And they found the clogging was typically in the top 1/4 inch of pavement. So it wasn't 2 inches, it wasn't 4 inches, it was just 1/4 inch, so just right on the surface. You just need to take that off with your regenerative air sweeper or your vacuum sweeper. And salt caused pavement degradation in isolated areas. There are some areas where the salt was brought in through cars or through some other means, and it caused pavement degeneration, so you do not want to salt permeable concrete. Next case study is permeable asphalt paired intersections in Robbinsdale. What they did is they designed paired intersections. I'll talk about this. This is one shortly after construction. I don't know how well this shows up, but you can see it's raining over here. And this is the non-permeable section, the conventional asphalt, and this is the permeable section. They had a specific interest, and that was there's a impairment study for Shingle Creek watershed. They're in the Shingle Creek watershed district. And the impairment study said that to protect the fishery in the Shingle Creek watershed district, they have to reduce salt by 81%. That's substantial. That's shocking, actually. What are your roads going to be like with 81% less salt? So they developed 2 permeable asphalt intersections, one over a sand subbase, one over a clay subbase. They were not salted during the winter, and they also identified 2 intersections that were replicates with them, except they were not permeable. The conventional asphalt sections were not salted, so they're comparing, were salted, so they're comparing unsalted permeable asphalt with a salted impermeable asphalt. That's the toughest comparison you can make. Sometimes it looked like this. There were times when the permeable unsalted section looked like this. This is asphalt that has no ice on it. And the impermeable salted section looked like this. Now that didn't happen all the time, actually. So there are some caveats to this. But there were times when they compared like this. And this is a fairly cold day, January 17th, 2010. What happened here is that they salted it. Everything started to melt during the middle of the day. It didn't melt enough to run off, which is kind of common, actually, if you think about it. I've known it to happen in my neighborhood. Everything didn't run off, and then it started to refreeze. And that is really dangerous surface to be driving around on, a refrozen driving surface. And so this is where it's refreezing right in here. Yeah, that's pretty slick. That's your ice skating rink. Permeable asphalt, this is all permeable pavement exposed here. You can find a place to drive on here. It didn't always happen this way. Sometimes the permeable unsalted section took longer for the snow and ice to melt than the impermeable section, especially in spring when it's warmer. It's not, it's not 10 or 20 degrees. It's like 35 degrees or something like that, or 34 degrees. This would melt slower than this. but I found this to be a striking comparison. And actually for this watershed and for many watersheds in Minnesota, this is a comparison you want to make. If you have an impairment in your watershed that's telling you you have to reduce your salt eventually by 81%, well, this is the comparison you're making. Here is a non-salted, impermeable asphalt, and here is non-salted permeable asphalt. This is the comparison that you have if you have an impaired watershed. This is your choice. So this is the main reason that I think permeable pavements should be coming to Minnesota. I think the salt and chloride issues are going to drive it. So the lessons learned from this study was, first, there's a similar amount, that's how they stated it, of bare pavement compared to salted conventional asphalt sections. Once again, the permeability of the subbase was important. We're always comparing sand and clay. You know, there's lots of permeabilities in between sand and clay. So we're comparing sand over here and clay over here. This works better than this, right? Well, what about the sections in the middle? You've got a lot of permeabilities in between sand and clay. So sand subgrade was more effective than clay for ice control. On clay, they had frequent overflows, and the water stayed longer in the clay. On sand, they infiltrated all the runoff, so the water would be moving through and then disappearing relatively quickly before it could freeze up. It'd get down to the area where temperatures were warmer because of the heat retained in the soil and the aggregate. Temperatures are warmer, it would sit there for a while, and then it would relatively quickly soak into the subgrade. So what Wank said, and when they did this study, is that permeable asphalt intersections have potential as an ice control management practice. We need to start working on this, start looking at it, start considering permeable pavement and its ability to control ice in the winter. So some conclusions. Well, construction and maintenance and design are critical to success. Of course, design would typically be good, but construction sometimes is not considered carefully. It's really important for permeable pavements. Maintenance is really important for permeable pavements, typically with vacuum or regenerative air sweepings. Permeable pavements can withstand Minnesota winters. This was a surprise. We knew some of that before we started, but it was a surprise at how well. We have 5 case studies, and all of them are withstanding Minnesota winters. It's really not a problem. Even on clay. There's a little more raveling on clay, but it's not that significant. And then the other thing that's important is that permeable pavements can maintain infiltration rates throughout the winter. So they may result in lower salt application rates in the winter months. I believe they will. I think this needs more investigation. So that's all I've got. What sort of questions can I answer?
So we have a microphone since this is being taped, and Hannah has a microphone. If you have a question, please just we'll pass the microphone over.
There are at least 34 people watching online, so it's not like you're talking. Nobody. Questions?
Oh, that's the question. So one thing I was wondering about what you said about how with movement it doesn't freeze, and you know we see rivers eventually freeze, and some Minnesota winters it just seems like it gets so cold that there should be maybe some freezing as that. Even as the water might hit the aggregate because it's so cold. So why is it that it stays active in the winter? That really surprises me.
Well, it actually was a little surprising to me too. I think that it doesn't stay in the pavement for very long, so there's not enough time for it to freeze in the pavement. and then it moves down into the aggregate, moves quickly through the aggregate, and then sits in the bottom to infiltrate. And sitting in the bottom, you're down where actually the soil is warmer. And so the soil is heating it continually. And so it must be that the heat coming from the soil comes up and continually keeps the water warm.
Interesting.
Yeah, right.
So have you done lab tests on that freezing aspect? Because that's just blows your mind when you think about it. So have you got documentation in that area?
We have not done lab tests, but there are lab tests that have been done on that. And I don't know if you want to talk about that, Lev?
Not on this.
Oh, okay, all right.
The EPA actually did a study on that in Chicago, looking at the base temperature, and it pretty much never dropped below 0 in any of those, or below 32 in any of those levels. So that's a published EPA study, too. So
Right,
let's look at that.
right. Of course, Chicago doesn't quite get quite as cold
I
as
think
Minnesota.
-7 was the coldest it got, so they really have nothing
Right.
in Minneapolis. but
-7
that's okay.
Celsius, right?
No, Fahrenheit.
Fahrenheit?
Yep.
Okay,
2008, that winter. So.
right, right. But even you get, when you get a real cold snap, I don't think it is, we have much snow during the real cold snaps. You know, when you think back over the winters, when it gets really cold, it doesn't snow. Usually it warms up and then it snows. And that's when the ice would be moving through fairly quickly. So.
Other questions?
I have a question about the subgrade aggregate that is being proposed. We're seeing a lot out in Carver County. A lot of people are using kind of the red rock just because it's cheaper. We're seeing some recommendations to use a granite. Do you have any preference on that or any recommendations?
Well, what has been stated is that you want an angular aggregate. And so you want something that's basically broken up rock. Not necessarily crushed, but busted up rock, and it's of the same size, fairly uniform size distribution. That way you maintain your voids, and the aggregate will provide a good base for the pavement. If you take river rock, it's not going to provide a good base for the pavement. It's kind of like, it's like, well, actually, river rock would be terrible for pavement, just like for any pavement, actually. So,
I think you mentioned in the talk too, but was there a certain size? You mentioned you wanted to have a uniform size. Is there like a certain size? Should it be like 3/4 inch size?
the sizes that are common would be roughly 1.5 to 2 inch to 3 inch size in the river rock, and then there's oftentimes a gradation between the surface where you have a smaller rock like 3/4 to 1.5 inch. So you start with 3/4 to 1.5 inch under the pavement, and then you move to the larger size.
Other questions? Or any comments on experiences?
Do we have questions from online, or can we do that? No?
We can do that, but we don't have any.
Okay.
So back there.
So I'm sorry I was late and I missed the majority of your presentation in the beginning, but experience, is this working? Experience shows if people are driving over the snow and packing it in, the ice builds up, so that's probably a maintenance issue to remove that hard pack. And we'll see how long that lasts this winter, but I've seen it already in that small snowfall that we had. And this is an alley situation where there's a snow plow, and then they drive over that pack, and then it's a thick chunk of ice. So I've always told people that it melts quickly, and the permeable pavers will be more dry than their pavement. But in that case, we'll see.
Right, and this talk was mostly about, actually was completely about permeable asphalt or permeable concrete. You know, where the whole surface is permeable, I don't know what would happen where most of the surface is impermeable, and then you have some little cracks with permeable pavements. So,
You mentioned on
If there's the microphone. That's for the web.
you mentioned TMDA chlorides impairments, and I was wondering how expensive it will be for cities or counties to implement or to become mainstream. Since this study seems kind of isolated from the mean, reality of what it is driving in winter. So.
well, I don't think it's isolated from the mean reality. I think that it's coming, and it will be expensive. It'll be expensive if we try and, it'll be expensive if we stop salting our surfaces as they are and put something else down. People don't like sand. It doesn't work very well. There is the possibility that a rock, kind of a very small chipped rock, could do a better job, but that's more expensive. But that's something that could do a better job. Still, that's not perfect. And the chloride problem in the Shingle Creek Watershed District is not unusual. That's very common. The regulators, the Minnesota Pollution Control Agency, is taking a fairly easy-handed line. They're taking a light-handed line with that because they know the implications of stopping salting. And so they have to slowly kind of get the communities to change. And so they're kind of taking it one step at a time. But eventually they will be there. And so we have to start looking forward. And the time to start looking forward is now. Because you can't change all your pavement to permeable pavement overnight. You have to take it one street at a time. So if we suddenly were told by the MPCA, Minnesota Pollution Control Agency, that we had to reduce our salt by 81%, it would be tremendously expensive.
Are there any studies in terms of residential use, like for a patio? How would you determine what percentage of infiltration you're getting and how successful the permeable pavers are?
For a patio, they are pretty successful. How would you determine percent infiltration? Well, then you need to put in a monitoring study, and that's actually pretty expensive. And that's where you catch the water that runs off. But most patios do a good job with the water.
As long as they're maintained.
As long as they're maintained, and as long as there are groundwater problems around. So
sandy substrate.
sandy substrate would be ideal.
Okay.
I'll ask another one just. Well, from my experience in Mille Lacs County, we have a lot of roads with maybe 10 or 12 inches of class 5 material underneath, which is fairly, I would say it's not too permeable, depending on the fines content in there. So it would hold water. So I'm kind of visualizing this design change. It's not just the surface design change, but we need a base design change, even maybe a new base material, specifically for permeable pavements, right?
I think that's true. I think that if your base material is not permeable, you need to find a permeable base material. So.
There's a question online.
Okay, good.
We have a question from one of our online viewers. The question is, did you see compaction in the subsurface aggregate where the subsurface aggregate became impervious? And if you did, what was the time frame where that compaction occurred?
Well, this was mostly a literature review, so we didn't see anything, but someone would have seen something, and what we found is a subsurface aggregate never experienced compaction of that type. because it's pretty large angular aggregate. It would be difficult to compact it.
So I have two questions. One is about, you showed the test track at Monroe, the loop, and also the freeway. And I was wondering, there's differences in traffic loads for residential versus for freeway. How does it perform in that regard? And my other question is about, is there a cost comparison between this versus standard pavement?
Okay, the first question is about freeways versus low-volume roads. I actually, although I could be wrong, I'm not a pavement designer, but I think that our current permeable pavement technology, it's probably not the right thing for freeways.
Do you know why, or-
Because of the loads. The loads and the volume of traffic on these freeways. And the permeable pavements just aren't made to handle that right now because of the lack of binder. The second question was...
About the cost, if a cost comparison for
Oh,
the city. And maybe
the
it's hard
cost
to say because
comparisons,
of the
yes,
salting is part
yes.
too.
Okay, thank you. Yes. Cost comparisons are all over the place. Some people say 10% more cost. Some people say 50% more cost. I myself have settled on about 20% more cost.
And does that include maintenance, or that's just the cost of the construction?
Construction costs.
Okay.
Construction costs. Maintenance, the difference in cost for maintenance should not be that much if you already accept that maybe you're using street sweepers, which are brush street sweepers, which are not good. You should move to regenerative or vacuum air, and that's regardless. That's the main cost, is buying these new street sweepers, because you should be sweeping your streets roughly every twice or multiple times a year anyway.
As a clarification of the online question, he was referring to the base material.
The sub-base?
Yes.
The sub-base? Yeah, in the diagram, it specified that you want uncompacted sub-base. You don't want to compact that sub-base, because that could create a problem. And if you put aggregate above it, fairly large aggregate, I don't think it's really going to compact the sub-base that much. It might compact it in certain locations slightly, but there's not that much compaction of the sub-base that's going to occur. That's what we've seen.
Any other questions or comments?
I have one more. Kind of looking at feasibility of, with on clay soils, usually these systems would have a drain tile. Is it possible for structural wise, so it doesn't break down over time, to suspend that drain tile and then you have a reservoir below it, so allow for infiltration, soil infiltration below the drain tile, and over time how that would affect the system?
Yeah, putting a drain tile in is what you need to do over clay soil, or something maybe close to a clay soil. I've thought about the possibility of people usually either put the drain tile at the top or the bottom, and I actually think in the middle might be better, so that you have some area that even if it is very slow infiltrating, you have some area to catch the water, and then let the water drain out. So I think that might be better, and it's not that close to the surface. So you may need a little more aggregate. Instead of 12 inches of aggregate, you may need 18 inches of aggregate. And then you put your drain tile in the mid-depth, and then if it gets above there, you let it drain out. That's what I would do.
Any other questions? All right, well, again, I'd like to greatly thank you
Okay.
for your talk.
Right.
All right, well, with that, I'd like to thank the guests who attended today.